This is part 3 of the PowerPoint slides, set 2A, and we are starting with slide number 64, water, which is it's a molecule composed of 2 atoms of hydrogen and 1 atom of oxygen. Water is very important in living things. Water is a polar covalent molecule. It has polarity, which gives it a lot of useful properties. Makes it very important for the human body and really for all living things on Earth. But the first thing chemically is that the bonds between the oxygen and the hydrogen atoms, we call them polar covalent bonds because the oxygen is a larger atom and it has a slightly larger pull on the electrons that are shared, giving it a slightly negative charge compared to the hydrogen atoms. So water is a molecule that has a slight positive charge on one end and a slight negative charge on the other end. So one thing you might notice is that when it rains on the windshield of your car, the rain forms droplets. Or if you spill water, it spills and forms puddles and little drops. And that is because the water molecules are attracted to one another. That is a property called cohesiveness. They are cohesive. They're cohesive because the oxygen end of one water molecule will line up and face the hydrogen end of another water molecule. The negative end of one is attracted to the positive end of the other. And that makes water molecules cohesive. And these dotted lines represent hydrogen bonding. That is bonding between the oxygen end of one water molecule and the hydrogen end of another. And this hydrogen bonding also allows some insects to walk on the surface of a pond or a lake, or even a large mud puddle, due to surface tension. So hydrogen bonding also gives us surface tension. And it gives us a lot of other properties too that aren't being named here. But it makes water an important solvent. The chemical reactions that occur in our cells, the chemicals have to be dissolved in water for those chemical reactions to occur. So water has a lot of properties because of its polarity and because of hydrogen bonding. Now in section 2.5, we're going to talk about chemical reactions and the ones that are most important to us in anatomy and physiology. In a chemical reaction, we have reactants and products. And I'm trying to find some that are not A's and B's. Okay, here's an example of a chemical reaction. We're looking at glucose, C6H12O6, reacting with 6 molecules of oxygen, and those together react to form 6 molecules of carbon dioxide plus 6 molecules of water, and then in the process, ATP is created. This is the chemical equation for the reaction that we call cellular respiration. Okay, so let's talk about what some of this means, some of the symbols. The reactants are glucose and oxygen. The products are carbon dioxide, water, and ATP. And in a molecule of glucose, we know it's one molecule because just like in algebra, that's an understood one. Okay, so we went over that glucose and oxygen are the reactants, carbon dioxide and water are the products. And then we need to look at reactions that release energy. If they give off energy, if they give off overall energy, then they are breakdown reactions or catabolic reactions. Okay, So we say that a reaction is exergonic if it releases energy or gives off energy. And it is catabolic reactions that do that. We say the reaction is endergonic if it requires energy, if it uses up energy. And those are anabolic reactions, or most of these reactions are synthesis reactions. They're reactions that build larger molecules. Now, a catalyst will speed up the rate of a chemical reaction. It'll cause it to go faster. Biological catalysts are enzymes. Enzymes are almost always proteins. So we say they're protein catalyst. Now we're moving into the Chapter 2, Part B slide set, and we're going to start with our larger molecules called macromolecules. So we need a few definitions. Biochemistry is the study of chemistry that involves living things, basically. So when we take in college, when you take your first basic chemistry class, we call that inorganic chemistry. So your basic chemistry class is inorganic chemistry, and that's going to deal with compounds like water, salts, acids, and bases. Now, there are some acids and bases that are organic, but these are water, salts, acids, and bases that don't contain carbon and hydrogen together. Now, I want to be clear about something because the notes make it confusing. All right. It says inorganic compounds do not contain carbon. That is not always true. Carbon dioxide is an inorganic compound, and it contains carbon. In order for a compound to be organic, it has to have carbon and hydrogen both. So it doesn't say that here. Make sure in your notes that you understand for it to be organic, not only does it contain carbon, but it also contains hydrogen. Carbon and hydrogen both. And these are our what we call macromolecules. They're the 4 classes of organic macromolecules. They are carbohydrates, fats, proteins, and nucleic acids. And fats can also be called lipids. Okay, for our inorganic compounds, we're going to start with water. And living cells are composed of 60 to 80% water. And water has some very important properties. Sorry. Water has a high heat capacity that enables it to hold in heat. It doesn't change temperature very fast. And that because our bodies are composed of such a large percentage of water, it helps us to maintain our body temperature. Water has a high heat of vaporization. And for us, what that means is when water evaporates off the surface of our skin in the form of sweat, it carries heat away with it, and it enables us to our bodies to cool. Water is a good solvent because it is polar. It is reactive, chemically reactive, and it also acts as a good cushioning agent. A lot of our body fluids that are mostly water help to cushion our organs and our the structures in our body. Okay, so high heat capacity means that it doesn't change temperature very fast. So it helps us maintain our body temperature. High heat of vaporization makes water a good cooling mechanism, useful as a coolant. Water is able to dissolve ionic compounds like salt and other polar covalent molecules like proteins. Okay, and this just shows you salt dissolving. Water is very reactive, and it's a component of hydrolysis and dehydration reactions, which we're going to learn about in a minute. And it also helps to cushion certain organs. It's a large component of CSF, or cerebrospinal fluid, which cushions the brain and spinal cord. Okay, salts are ionic compounds, so it doesn't have to just be sodium chloride. It can be magnesium bromide or calcium, I don't know, iodide. But a salt is going to be a positively charged ion and a negatively charged ion. So here are some examples of salts in the body. Besides sodium chloride, which is table salt, we also have calcium carbonate, potassium chloride, different calcium phosphates. So this is always a cation combined with an anion. And the ions that form when these salts dissolve in water are called electrolytes. Now, acids and bases are electrolytes, but acids donate protons or hydrogen ions. The reason we can call hydrogen ions protons, they can either be called a proton or they can be called a hydrogen ion, because all a hydrogen ion is simply a proton. It has lost its electron and now it just has the one proton. So a hydrogen ion has a plus charge, and all it really is a proton. So an acid is any compound that when it dissolves in water, it donates hydrogen ions or protons to the solution. So important acids are hydrochloric acid. Notice all of these acids have a hydrogen at the beginning of the chemical formula. Acetic acid or vinegar, carbonic acid. These last two, acetic acid and carbonic acid, are organic. Do you see why? Both of them contain carbon and hydrogen. Carbon and hydrogen. When you have carbon and hydrogen together, that's organic. Then we can have bases, and bases, instead of donating protons or hydrogen ions, they're going to remove hydrogen ions from solution. So an example of a strong base is sodium hydroxide. Now, a base also will donate hydroxide ions, which is OH minus. Or here they call it hydroxyl ion. Hydroxyl or hydroxide, either one is fine. A hydroxyl ion or hydroxide is given off in solution by a base. But we can also say that bases remove hydrogen ions from solution. Instead of proton donors, we call them proton acceptors. So important bases in the body are bicarbonate ions and ammonia. Okay. The pH scale measures the level of hydrogen ions, or the concentration of hydrogen ions in solution. So if the number is low, if it's below 7, that's going to tell us that it's an acid. And if it's above 7, that's going to tell us it's a base. And we can also compare solutions. So let's say we have a solution that has pH 5 compared with one that has a pH 6. The solution that's pH 5 is 10 times more acidic than pH 6. Or we could say pH 6 is 10 times less acidic than pH 5. So every time you go up 1, it makes it 10 times less acidic. Or if you go down 1, it's 10 times more acidic. Acidic solutions have a pH less than 7, so a low pH. High concentration of hydrogen ions, but low pH. And then an alkaline or basic solution has low hydrogen ion concentration, but high pH, above 7. And here's some common substances and their pH values. The strongest base, which has the highest pH, is sodium hydroxide. A weaker base is blood, which has a pH of 7.4. It's almost neutral. A very weak acid is milk, pH between 6.3 and 6.6. So it's an acid, but it's a weak acid. It's a much weaker acid than hydrochloric acid or stomach acid, which can have a pH of 0 at its strongest. Lemon juice is a very strong acid as well, and then wine and coffee. A neutralization reaction is when you have a base and an acid. They're always going to form a salt and water. So when you mix a base and an acid, you get a salt and water. That's a neutralization reaction. And then buffers, and I don't really know why this looks weird, but basically you have, this is a buffer system, a carbonic acid buffer system. But a buffer is a system of chemicals that resist changes in pH, and our body has a lot of buffer systems. The carbonic acid buffer system will donate hydrogen ions if our blood pH is high. It'll make it lower, and it will remove hydrogen ions if our blood pH is too low, and that'll make the pH higher.